Okay, welcome everyone. Matt is going to be telling us about constructing quantum vertex coalgebras from Yangians. Take it away, Matt.
Okay. Yeah, thank you for the invitation to speak. So what I'd like to present today is how we can construct two examples of structures of quantum vertex coalgebras on Yangians, and how we can induce from these structures quantum vertex algebra structures on a space called the dual Yangian. And so this is based on ongoing work with Alex Weeks and Curtis Wendland. And so I'll start by just giving some background on what quantum vertex algebras are and what they look like, as well as quantum vertex coalgebras. So if you think about a vertex algebra as something like a family of vertex operators or quantum fields acting on a classical space, like the vacuum module of an affine Lie algebra, then you can think about a quantum vertex algebra as something like a family of vertex operators acting on a quantum space, for example, like the vacuum module of the centrally extended Yangian double. And there are generally two examples that we consider. The first are quantum vertex algebras living on complex vector spaces or on modules over formal power series, right? So the first examples were introduced by Frankel and Reshidikin, and they introduced them in 1997 under the name deformed chiral algebras. And you can think about these as families of vertex operators on a space where the vertex algebra axioms are being deformed by a solution of the quantum Yang-Baxter equation. And the second example, which I'll call H-adic quantum vertex algebras, these are the examples that I'm going to be talking about today. These were introduced in 1998 by Eddinghoff and Kasdan. They were motivated by the work of Frankel and Reshidikin, and these are families of vertex operators living on a topologically free module over a formal power series ring. And their relations are also deformed by a solution of the quantum Yang-Baxter equation. But more than that, you can think about them as formal deformations of vertex algebras, in the sense that if you quotient out by h bar v, you get a true vertex algebra. So this is kind of mirroring the deformation theory for Hopf algebras. Okay, and most of the literature on quantum vertex algebras right now, it concerns constructing examples primarily. And constructing examples for quantum vertex algebras is actually extremely difficult. So for vertex algebras, you have this nice theorem called the reconstruction theorem. It basically says, if you have a vector space, you have a family of vertex operators on it, a vacuum module or a vacuum vector, and a translation operator, all of which satisfy the axioms of a vertex algebra, and the coefficients of your vertex operators acting on the vacuum vector, if they span the field, span the vector space, you have a true vertex algebra, okay? So this kind of says you only need to check the axioms on generators, right? The analog of this theorem for quantum vertex algebras isn't known, and it seems like it's probably difficult to show. And so you can imagine, if you don't have this reconstruction theorem, how much harder it would be to construct vertex algebras, because you can't check the axioms on generators. You have to check them on every field associated to every vector. Okay, and so this is a big problem. And it seems like quantum vertex coalgebras might be easier to construct than quantum vertex algebras, and I'll get into why that is. And it also seems like we might be able to use quantum vertex coalgebras to construct examples of quantum vertex algebras. Okay, so like I said, these are vertex operators on a module over formal power series ring with relations deformed by a solution of the quantum Yang-Baxter equation. So I would just like to, take a few minutes to explain what all these words mean, and just a little bit of background so I can kind of write down a definition that'll make sense to everyone. So I'll just denote by K, foremost power series ring in H bar. And if V is a K module, we call it topologically free if it's really just a formal power series ring with coefficients in a vector space and the obvious action where H bar just kind of ignores the coefficients in W. And we'll equip V with the H-adic topology. And for our purposes, all you really need to know is that the family of submodules, H bar to the n times V, for n greater than or equal to 0, form a basis of open neighborhoods of 0. And so, when you're talking about vertex algebras, things like the truncation axiom, you want to know when things go to 0. For quantum vertex algebras, things go to 0 in the H-adic topology. Okay, so that's really all we need to know from this. Okay, and an operator S satisfies the quantum Yang-Baxter equation if it satisfies this equation star. And S is a operator on V tensor V, while this equation is an equation living on the triple tensor product of V. So we need to know how we're viewing S as an operator on this triple tensor product. And we do this with the subscripts. So for example, S12 indicates you're acting on the first two components. So it's just S tensor ID. S23 is acting on the last two components. So it's just the identity tensor with S. And S13, you think about it as acting on the first and third component, which we can represent in the way I've written here, where tau is just the permutation operator. Okay. And for vertex algebras, we'll actually need solutions which are unitary. A lot of basic results just don't hold if you don't have a unitary solution. And so this means it's invertible, and the inverse is given by S21 of negative Z. Okay, so just a simple example here. If you take C to the n for some n, then you can define R, a solution R, as being the identity on V tensor V minus H bar tau over Z. And if you choose any fixed basis of Cn, then the permutation operator tau you can just represent as the sum over these Eij tensor Eji, where these are the component matrices with respect to your fixed basis. Okay, and so this solution is it's one of the simplest non-trivial solutions of the quantum Yang-Baxter equation. It's called Yang's solution, and it's very important for vertex algebra, for Yangians. And this is not a unitary solution, but you can rescale it by just some power series to get a unitary solution. Okay, and if you look at the literature on quantum vertex algebras, they're often building vertex algebras on a space called the dual Yangian, and they actually use this solution. So this is a particularly important solution for quantum vertex algebras. Okay, so what does a quantum vertex algebra actually look like? Well, it's a topological state field correspondence with extra structure. Topological here meaning, is referring to the H-adic topology. So it's a topologically free K module equipped with a vacuum vector, a translation operator, and a state field correspondence, satisfying the usual truncation unit that should be creation and translation covariance axioms. And here I'm using a slightly different notation. We're viewing Y as an operator from V tensor V into formal power series with coefficients in V, instead of an operator from V to formal power series with coefficients in NV. The reason we do this is because the locality condition, for example, becomes deformed by a solution of the quantum Yang-Baxter equation. And this notation works much better with the insertion of that solution of quantum Yang-Baxter equation into our axioms, okay? And when you translate these axioms into the usual notation for vertex algebras, you'll see they're the exact same as vertex algebras, except for the truncation axiom, where now we're not saying that the sequence U n of V goes to 0, as n goes to infinity, it goes to 0 in the h-adic topology. Okay, and so that's all this axiom is saying. It's just translating things into the language of K-modules. Okay, and so a braided vertex algebra, or an h-adic braided vertex algebra, this is a topological state field correspondence equipped with a solution of the quantum Yang-Baxter equation. And we want to choose them such that the kind of scalar component with no h bar is the identity. And we impose a few restrictions. First of all, we want to have shift conditions that kind of tell us how the translation operator commutes with S. And we have a deformed locality condition, which we'll call S locality. And so all this is really saying is that for any natural number n, the locality condition for vertex algebra holds mod h bar to the m up to an insertion of this S operator. So on one side, you're precomposing with S. Okay? And a quantum vertex algebra is a braided vertex algebra where we impose this hexagon relation. So this kind of tells you how S intertwines with your vertex operator, so your state field correspondence. And the point is, for vertex algebras, you have these nice associativity conditions associativity properties that are satisfied by the state field correspondence. For braided vertex algebras, these are not satisfied. You need to impose an extra condition. So if you impose this hexagon relation, what you find is that for any natural number m, the kind of natural associativity condition holds mod h bar to the m. In some papers, you'll see that they just define a quantum vertex algebra as one in which this associativity condition holds. Okay, and our second players are vertex coalgebras. I won't write down exactly what vertex coalgebras are, but I will write down what quantum vertex coalgebras are, and you can just mod out h bar to get the definition of vertex coalgebras. So these were introduced by Keith Hubbard in 2004. He was actually a PhD student at the University of Notre Dame when he did this work, and he introduced these objects with some motivation coming from string theory and conformal field theory. And they consist of a vector space. Here I'm talking about vertex coalgebras on complex vector spaces. So you have a linear functional from V to C, a kind of translation operator D, and a state cofield correspondence. So here C is playing the role of the vacuum vector, D is playing the role of the translation operator, and of course the cofield correspondence plays the role of the state field correspondence. The main thing to notice here is that your state field correspondence, state cofield correspondence, your cofields, these are not formal power series in Z. They're formal power series in Z inverse. And so this causes a lot of problems and can kind of cause these things to be pretty poorly behaved. So we'll end up imposing extra structure to kind of make them nicer. And so like quantum vertex algebras, quantum vertex coalgebras can be thought of as vertex coalgebras where their axioms are deformed by a solution of the quantum Yang-Baxter equation. And we actually already have some pretty interesting examples of quantum vertex coalgebras in the case of complex vector spaces. So in 2022, Alexei Latintsev introduced, or he showed that cohomological Hall algebras actually admit a compatible quantum vertex coalgebra structure. And so by this, I mean they're quantum vertex coalgebras where the state cofield correspondence is actually an algebra homomorphism. And in 2023, Henry Liu showed that K-theoretic Hall algebras admit compatible quantum vertex coalgebra structures as well. But here they have a like multiplicative solution of the quantum Yang-Baxter equation rather than an additive one. And so some of the other axioms change as well, but not too much. And so here we can start to see why it might be easier to construct quantum vertex coalgebras than quantum vertex algebras. despite neither of them having a reconstruction theorem. It's because we're building quantum vertex coalgebras on spaces of algebras where our state cofield correspondence are algebra morphisms. So you only need to show the axioms hold on the cofields corresponding to algebra generators, which is much easier than showing it for all of them. And there's a very nice theorem of Hubbard, which says that if you have a z-graded vector space, which is truncated below with finite dimensional graded components, then you can choose a distinguished vector, so a vacuum vector, a translation operator, a state field correspondence. And if on the graded dual, you let C be the double dual of the vacuum vector, D the pullback of your translation operator, and you define your state cofield correspondence by this equation star. This is kind of the most, I think, obvious way to define it. Then V is a graded vertex algebra if and only if V prime is a graded vertex coalgebra. And similarly, you can start with the structure of a vertex coalgebra defined on the graded dual, structures of a vertex algebra. You have a vertex coalgebra if and only if the graded dual is a vertex algebra. Okay, and so this leads us to kind of two very natural questions for quantum vertex algebras. And so these questions are, first of all, the examples I mentioned before, these are on complex vector spaces. As far as I know, there are no examples in the literature of H-adic quantum vertex coalgebras. So the first question, of course, is, are there interesting examples of quantum vertex coalgebras, H-adic quantum vertex coalgebras? And can we generalize Hubbard's theorem to construct quantum vertex algebras? And what I would like you to take away from this talk is that, first of all, there are interesting examples of H-adic quantum vertex coalgebras. The Yangian is an example. And at least in this example, we can generalize this theorem. So we can construct, through a duality operation, quantum vertex algebras from the quantum vertex coalgebra structures of the Yang. Okay, so I'd like to just give you a feeling for what quantum vertex coalgebras actually look like. So they're topological state cofield correspondences. So they're topologically free K modules. They have these operators CD and the state cofield correspondence, and they satisfy four axioms: truncation, co-unit, co-creation, and d-derivative. If you go through them, you can kind of see exactly how these are inspired by the axioms of a vertex algebra. They don't really, they're pretty closely related. And in the truncation axiom, this sequence delta n of v goes to 0 as n goes to negative infinity in the H-adic topology instead of positive infinity. So our cofields are Lorentz series in Z inverse, not in Z. Okay. And a braided vertex coalgebra, again, just like quantum vertex algebras, it's a state field correspondence, state cofield correspondence with a solution of quantum Yang-Baxter, where your solution is kind of intertwined in a certain way by the operator D, and you have a co-Jacobi identity that holds. The reason we start with the co-Jacobi identity and not like co-locality is because the co-locality condition actually changes quite a bit for, well, a little bit for vertex coalgebras. And so, I mean, if you look at this co-Jacobi identity, you'll see it looks a lot like the Jacobi identity for vertex algebras, except now you're pre-composing with, so you're composing with this operator S. For quantum vertex algebras, for example, you pre-compose one of your terms with the operator S. And a quantum vertex coalgebra, well, it's a braided vertex coalgebra with this hexagon relation. We impose it for the exact same reason. The nice like co-associativity conditions that you want don't hold without it. Okay. And so when you're developing the theory of vertex algebras, a lot of very basic results are derived by starting with your Jacobi identity. You multiply by some power of zx or w, you take a residue, you show a term vanishes, and you derive these conditions, right? But these state cofield correspondences, they're Lorentz series and Z inverse. So you can never multiply by a power of Z to make a residue vanish. And so a lot of these properties that follow very nicely from the Jacobi identity for vertex algebras, you simply can't get them from the co-Jacobi identity without some additional structure. And so what we want to do is we need to impose a graded structure on the space, and we need to evaluate by a homogeneous vector in the dual space, and then we can get things to vanish. So I'll just mention quickly how we impose gradings on quantum vertex coalgebras, and then I'll talk a little bit about some properties of these objects. So a K-module V, we call it Z-graded if it admits a dense Z-graded C of H submodule, where each VK is, and we'll call such a Z-graded module truncated if it's truncated below. And we call a braided vertex coalgebra V-graded if it's Z-graded as a K module, it's truncated, and these delta K operators appearing in the state cofield correspondence, we want them to have degree K plus 1. Okay, and what we're going to need to do is we're going to need to construct graded duals. And so the way we do this for K modules is we let Jm be the H-adic completion of the sum of these terms with index greater than or equal to m. The H-adic completion, you should think about it as something like a K module doesn't necessarily have limit points of all Cauchy sequences. And so you want to construct a space containing the space you start with where you incorporate those limit points, right? And so when you take these H-adic completions, give you a descending filtration on your space V. And then the graded dual, we define it as the operators in the K-linear dual such that for any n, f of jm is like a scalar multiplied by h bar to the n for m sufficiently large. This is a little bit easier to understand if you think about just the graded components. This is Z-graded, and a map in this space is degree L if it sends something of degree K to a scalar multiple of h bar to the L plus K. Okay? So what does colocality look like for these objects? Well, if V is a graded braided vertex coalgebra and phi a homogeneous vector, then for any natural number m, colocality, the usual kind of the condition you would expect, holds mod h bar to the m up to evaluation by this homogeneous vector. So the point is, we can't just take residues of the co-Jacobi equation and and derive equations. We actually need to evaluate by some homogeneous vector, mod out h bar, and then we can start showing that residues vanish. And similarly, we have the co-associativity condition, which holds if you are a graded quantum vertex coalgebra. So we need the hexagon relation. And this says for some homogeneous vector and some natural number m, the kind of natural co-associativity relation holds mod h bar to the m after evaluation by h bar. And so these conditions, they appear to be quite a bit weaker than locality and associativity for vertex algebras, but actually they are strong enough to give equivalent characterizations of quantum vertex coalgebras. So the co-Jacobi identity can actually be replaced in the definition of a graded braided vertex coalgebra by locality and the D bracket, and this is the form that the D bracket takes for quantum vertex coalgebras, or it can be replaced by co-associativity and skew symmetry. And if you're a quantum vertex coalgebra, then you can just replace the co-Jacobi identity by these colocality conditions. And when I talk about the quantum vertex coalgebra structures on the Yangian, we actually show that they satisfy, I won't show that they satisfy it, but in our proofs, we show that they satisfy co-associativity and skew symmetry. So we actually use these equivalent characterizations.
Matt, a question. Are you saying in the
Yeah.
second part that you don't need D? You don't need the D bracket in that setting? Is that?
Yeah. Yeah.
Okay. Can you say
So
a little more about that? Sorry.
so the way you prove these things is, so for vertex algebras, you go through these rationality properties and you show like rationality follows from locality and associativity, and then associativity follows from locality and the D bracket, and all of this. And so for quantum vertex coalgebras, it's the same. If you're a quantum vertex coalgebra with locality, you get associativity. And so then the Ko-Jacobi equation follows.
Gotcha.
And from the Ko-Jacobi equation, you get the D bracket. Yeah.
I see.
So
Thank you.
it's very similar to vertex algebras.
Thank you.
Okay, and so I want to build structures of a quantum vertex coalgebra on the Yangian. So I'm going to, for the purpose of this talk, I'll just present things in terms of SL2, but every statement I give holds for any finite dimensional simple complex Lie algebra. Okay, so the Yangian of SL2, it's the unidal associative K-algebra generated by these three families, three infinite families of generators, HR, XR plus, and XR minus, where R is a natural number. And they just satisfy these relations here. And actually, you can show that the Yangian is generated by X0 plus, X0 minus, H0, and H1. And the standard bialgebra structure on the Yangian is given by taking X0 plus minus to be primitive. So that's just delta X is X tensor 1 plus 1 tensor X, and the co-unit evaluates to 0. And the co-unit on H0 is 1, and on H1 it's 0. The coproduct on H0 is like a primitive element, and the coproduct on H1 is defined in this way. So it's fairly simple on these generators, but there's no explicit formula for arbitrary HR or arbitrary XR plus minus, because the relations just become too complicated. And so when I construct these quantum vertex coalgebra structures, I'm actually going to need something called the formal shift homomorphism. And so this is just a map from the Yangian to polynomials with coefficients in the Yangian. And so what it does is it takes, for example, HR, it sends it to a degree R polynomial in Z with coefficients are scalar multiples of HK, where K runs from 0 to R. And the same for XR plus and XR minus. Then we can define the shifted coproduct by composing the coproduct with this shift homomorphism tensored with the identity. Okay, and so I will claim that we can put some additional structure on Y such that this map gives us a quantum vertex coalgebra. And this example is quite trivial because it just goes into polynomials, right? So this is like a co-commutative example, but the next example that I write down will not be co-commutative, and it's actually a fair bit more complicated. So let H of Z be the formal power series with coefficients, just the generators Hn. Then we can define something called the shifted Drinfeld coproduct, which is a map from the Yangian into formal formal Lorentz series in Z inverse with coefficients in the Yangian. And here, when I say like series, I mean they go to 0 in the H-adic topology as Z goes to infinity, right? And so the shifted Drinfeld coproduct, it's defined on the generators in the way I've written here, and it's actually an algebra morphism. So we only need to define it on generators. And this might look a little bit unnatural. Why would you define it this way? It actually comes from a Drinfeld coproduct on the Yangian double. On the Yangian double, you can kind of similarly collect all of your generators as formal power series, and then you can just kind of naively say, okay, well, I'm going to pretend these formal power series are elements of my algebra, and I'll define a coproduct on them that looks basically identical to the coproduct on Drinfeld-Jimbo algebras. So it's kind of a very simple and naive construction. It actually doesn't quite work because the coproduct has infinite sums in it, so it's not really a coproduct. But you can compose it with this shift to get a coproduct to form a Lorentz series where now the coefficient of each z is a finite sum. So you get kind of like a true algebra homomorphism into the space of formal Lorentz series and z inverse with coefficients in the tensor square of the Yangian. And so there's a theorem by Drinfeld that there does exist a solution of the quantum Yang-Baxter equation with coefficients in the tensor square of the Yangian. His proof was, it wasn't constructive. It was like a cohomological proof. And there is a constructive proof of this, the existence of this thing now, but it's highly non-trivial. So the existence of this thing is highly non-trivial. And so we can use this to endow the Yangian with the structure of a quantum vertex coalgebra. So first of all, there exists an endomorphism on the Yangian, which you can think about as something like the logarithm of the shift homomorphism. And then with the shifted coproduct coming from the standard coproduct, you take C to be the counit, you take D to be this like logarithm of tau z, and then your S matrix, your solution of the quantum Yang-Baxter equation, is not R, but rather add R, where you conjugate by R and its inverse. Okay, and for the shifted Drinfeld coproduct, you also get a quantum vertex coalgebra structure, but here you need to take R0 of Z. R0 of Z is kind of like the centerpiece of the Gauss decomposition for R. You can kind of think about this as like some matrices have an LDU decomposition where they're a product of a lower triangular, diagonal, and upper triangular matrix. And this is like the diagonal part of an LDU sort of decomposition for R. And so we would like to take these quantum vertex coalgebra structures and build quantum vertex algebra structures on the dual Yangian. So what exactly do I mean by the dual Yangian? To kind of define the dual Yangian, it actually comes from something called the Drinfeld-Gavrini subalgebra. So to define the Drinfeld-Gavrini subalgebra, we inductively define these operators delta n, where delta 0 is the counit, delta 1 is the identity, and delta n is just defined by this formula where delta is now the standard coproduct. Then the Drinfeld-Gavrini subalgebra is this very unnatural looking thing, which we'll denote by y dot, and it's the case subalgebra of the Yangian consisting of those elements where if you evaluate by this operator delta n, and then you evaluate by the nth tensor power of the identity minus epsilon, then you get something that has an h bar to the n appearing in it for every n. And we'll denote by y dot, where we just drop the brackets, the h-adic completion of this space. So this is a topologically free n-graded K module. And because it's n-graded, we can take its graded dual, and we call the graded dual the dual Yangian. Now, the reason we want to think about this space in particular is because there's a lot of literature on quantum vertex algebras where people are constructing quantum vertex algebras on the dual Yangian, or the vacuum module of the Yangian double. So their dual Yangian is not this one, it's a subalgebra of the Yangian double, but this dual Yangian is equivalent as a topological Hopf algebra to like a minor coalgebra twist of the dual Yangian as a subalgebra of the Yangian double, right? So the point is, we want to be able to compare the quantum vertex algebras that we construct to existing quantum vertex algebras in the literature. Okay? So this space admits the structure of a Z-graded quantum vertex algebra. And here we take the vacuum vector to just be the, C should actually be the counit, right? So the vacuum vector is just the counit. T is the pullback of this operator D I introduced earlier. And the solution of the quantum Yang-Baxter equation, this is the pullback of the solution of the quantum Yang-Baxter equation for the Yangian, right? This add of R of Z. Then we can define our state field correspondence in this kind of, I think, the most obvious way you would define it on the dual. And then this actually does give you a Z-graded quantum vertex algebra. And so here we can take the state cofield correspondence to either be the shifted coproduct or the shifted Drinfeld coproduct. When you take the shifted coproduct, you get a commutative quantum vertex algebra. We think that this commutative quantum vertex algebra is equivalent to one which appeared in the thesis of Matteo Gardini. But it's a little bit hard to compare because the presentations of these spaces are so different. And we think that the quantum vertex algebra you get from the shifted Drinfeld coproduct is something new. And so I'll finish off on just a couple questions or thoughts. So we know that this construction of the dual Yangian is equivalent to the construction that's typically used in the quantum vertex algebra literature, but it's difficult to translate what the state field correspondence looks like in the other presentation. And so that's something we would like to figure out so we can really directly compare to existing literature and say, like, this is actually really, it's something new. The second thing is that in the work of Alexei Latintsev that I mentioned before, he talks a little bit about something called quasi-triangular quantum vertex bialgebras. And so these are kind of natural generalizations of quasi-triangular Hopf algebras or quasi-triangular bialgebras where you have a algebra with a quantum vertex coalgebra structure where your the failure of your quantum vertex coalgebra structure to be co-commutative is controlled by an R matrix. And so we think that these examples actually fit into that setting where these are probably something like a quasi-triangular quantum vertex bialgebra. So there should be a lot, some interesting things to say there. Okay, so I'll finish there.
Thank you so much, Matt. Let me stop the recording and we'll open it up for questions. Thanks.